Okay, hi everyone. Today we'll be looking at how to solve for the states in a state space system, and in the process we'll also introduce what is called a matrix exponential, and we'll see how to solve for the matrix exponential. So let's start with a simple scalar system, x dot equals ax. Now if we want to get a closed form expression for x of t, then what we do is just integrate this. So we have integral dx by x from x of 0 to x of t equals a times integral 0 to t dt. So you solve this and you get x of t equals x of 0 e power at. So this is simple because it's a scalar homogeneous system without any inputs. So given a general LTI system, x dot equals ax plus bu, we want to arrive at a closed form expression for x of t as some function of the initial states x of 0 and the input u of t, and of course the system matrices. Now how do we go about doing this is to take the Laplace transform of the state space representation. So we get s x of s minus x of 0 equals ax of s plus b u of s, and we all know we can solve for x of s as Si minus A inverse x of 0 x of 0 plus Si minus A inverse B u of s. Now to take this back to the time domain, we take the inverse Laplace transform. In order to do that, we need to know what the inverse Laplace transform of this function here is. So we use this expression that now you can check for yourselves that this is true, because if you pre-multiply by Si minus A, then you get identity. So using this, Laplace inverse of Si minus A inverse is I plus At plus A square t square by 2 factorial and so on. Now this is similar to the scalar exponential expansion, which is e power at is 1 plus at plus a square t square by 2 factorial. So this is what we call the matrix exponential, e power at. Note that A is a matrix. So using that, and from here we say that x of t equals e power at x of 0 plus integral 0 to t e power at minus tau b u of tau d tau. Now the second part of this expression we get by using the property that multiplication in the S domain corresponds to convolution in the time domain. So this is the closed form expression for your state x of t as a function of your input, system matrices, and the initial conditions. So the question now is, how do you compute this exponential matrix exponential e power at, because it's an infinite sum of matrices. Now the first method is quite obvious from the way we saw here, that e power at is just the Laplace inverse of Si minus A inverse. So given a matrix A, you can just compute Si minus A inverse and take the inverse Laplace transforms of the elements of the matrix, and you get the matrix exponential. That is one method. The second method is by using diagonalization. So here we assume that the matrix A has distinct eigenvalues, in which case it can be written as A equals some PD P inverse, where your D is a diagonal matrix with entries lambda 1, lambda 2 and so on lambda n, where these are the eigenvalues of the A matrix. So once you, why we do this diagonalization is because we can see that if we express e power at in terms of as something times e power dt, then your e power dt is easy to compute because it's a diagonal matrix. So we see how we do that. You know that e power at is and now we know A is P D P inverse. So by the way, P is any invertible matrix that accomplishes this diagonalization of the matrix A. You can choose P to be the matrix of eigenvectors for distinct eigenvalues. Yeah, so A is P D P inverse. A square is just A into A, which is P D P inverse into P D P inverse, which turns out to be P D square P inverse. Similarly, A cube is A square into A, which is P D square P inverse into P D P inverse, which is again P D cube P inverse. So in general, we can say that A power k is P D power k P inverse. So going back to the original matrix exponential, e power at is I, and we express the identity matrix as P into P inverse plus A into T, and A is P D P inverse into T, plus A square, which is P D square P inverse T square by 2 factorial, and so on. So we just do some jugglery here. So take P and P inverse on either side outside. So you have I plus dt plus d square t square by 2 factorial, and so on. So we basically have that e power at equals P e power dt P inverse. So since D is a diagonal matrix, we can use this way to compute the matrix exponential e power at. We'll now look at the third method. So the third method for computing the matrix exponential is using the minimal polynomial. Now given a matrix A, from Cayley-Hamilton theorem, we know that the matrix satisfies its characteristic equation. So let's say f of lambda equals determinant of lambda I minus A equals 0 is the characteristic equation of the matrix A. So we know that f of A equals 0. Now for an n cross n matrix A, this polynomial is of order n. But there could be a polynomial of lower order for which the matrix satisfies. So let's say there is another polynomial phi of lambda, which is say lambda per n plus a1 lambda per n minus 1 so on. So this m is less than or equal to n, and this polynomial is such that phi of a equals 0. So it's called a minimal polynomial if the for the smallest m for which the matrix satisfies this equation, phi of a is 0. Now for all computational purposes we can just use this. Phi of lambda equals determinant of lambda I minus a, which is nothing but the characteristic equation divided by some d of lambda. Now this d of lambda is the greatest common divisor of adjoint of lambda I minus a. Now why do we use this to find exponential of at is we use this formula called the Sylvester interpolation formula, which basically says that a phi of lambda which is the minimal polynomial of a matrix A, assume that it is in this form and let's say its roots are lambda 1, lambda 2 and so on, lambda m. So in that case your matrix exponential can be expressed using this formula. So basically this whole thing is a matrix. You find the determinant equated to 0 and one of the entries is e power at. So we get e power at in terms of all the lower powers of a until m minus 1. So we'll see how these three methods work with an example. So we'll start with the first method, which is just using inverse Laplace transforms. So Si minus A is and minus C. To find the inverse, Si minus A inverse, you first calculate the determinant, which turns out to be just the product of diagonal terms, s minus 2 whole square into s minus 1. So and then your Si minus A inverse is adjoint of Si minus A by determinant. Okay, so adjoint of Si minus A. And then you get Si minus A inverse is adjoined by the determinant, which is and e power at is the inverse Laplace transform of this. So, inverse Laplace transform of 1 over s minus 2 is e power 2t. Similarly, you take inverse Laplace transform of every element in the matrix. We know how to compute the inverse Laplace transform of this by expanding it in terms of partial fractions. So that will just be 3 times e power 2t minus e power t. So that's the matrix exponential computed using inverse Laplace transforms. We will solve it using the minimal polynomial way as well. So to do that, like I had mentioned, you find the minimal polynomial first, which is determinant of lambda I minus a by d of lambda. Now, so we know that adjoint of Si minus a is this, and clearly S minus 2 is a common factor of this adjoint matrix. So your d of lambda equals S minus 2, and we know determinant of lambda I minus a is S minus 2 square into S minus 1. So, so we have phi of lambda equals lambda minus 1 into lambda minus 2. So we know our lambdas here, lambda 1 is 1, lambda 2 is 1 again, 2. And we use this formula to calculate e power at. So you can just substitute here. So here your m equals 2 because phi of lambda is of order 2. So you have 1. So you can solve this determinant equation the way you usually solve for determinants and get e power at in terms of a and these exponentials. You can cross check that you get the same answer as this. Now going to method 2, which is diagonalization. Okay, so method 2 including diagonalization, the matrix, so firstly we find out the eigenvalues of the matrix A. We have determinant of Si minus A here. The eigenvalues are 1, 2 and 2. There is a repeated eigenvalue which is 2. Now the matrix P, which is used for diagonalization, is a matrix of eigenvectors V1, V2, V3. So we solve for these eigenvectors for each eigenvalue. Say for lambda equals 2, AV equals 2 2v, this is just lambda, AV equals lambda v will give you so when you solve this, you get 2v1 equals 2v1. So here we see that our eigenvector v is of this form, v1, v2 and 3v2. So there are no constraints on the quantity on the first and the second coordinates. So you see that the null space for this eigenvalue, which is lambda equals 2, has dimension 2. So basically what I am saying is that for eigenvalue 2, you will have 2 eigenvectors because 2 quantities are not constrained. So you can just put in any values for v1 and v2. I will just choose so these are the 2 eigenvectors corresponding to the repeated eigenvalue 2. Now we compute for lambda equals 1. So solving this equation, you get that v1 equals 0, v2 equals 0 and v3 can be any real number. So we choose our eigenvector to be 0, 0 and 1. So your matrix P finally looks like 1, 1, 3, the first eigenvector, 1, 2, 6, the second eigenvector, and 0, 0, 1. So from here you can compute P inverse as the regular adjoint by determinant. I will give you the numbers. Okay, so once you have P and P inverse, you can your D is nothing but a diagonal matrix with these eigenvalues. So note that the eigenvalues need to be in the same order as your eigenvectors. So these two eigenvectors correspond to lambda equals 2, so 2 and 2, and this is for lambda equals 1, and the remaining entries are all 0. So once you have, again here you can cross check that P, D, P inverse will give you A. And from here your e power dt is e power 2t 0, 0, 0 power 2. So that's just the individual exponentials along the diagonal. So once you have e power dt, you compute e power at as p e power dt p inverse, and we had obtained our e power at earlier on using the other two methods before. So you can again check that it matches with the value that you get here. So yeah, so today we learnt about why we need matrix exponentials and how do you compute them using an example. Thank you.